Hello, this is the fourth and last segment on random walks. We ended the last segment with the observation that the distance from the origin seems to grow with the number of steps, but that we didn't have any good intuition about quite how fast. I want to start today's segment by drawing a plot that will give us some intuition about that. If we look over here at the code, we'll see that I've replaced drunk test by something called drunk test P. This is essentially the same as drunk test, except rather than printing something on the screen, I'm producing a plot. Also, to simplify the plot, I'm ignoring the maximum and minimum distances and only plotting the mean for each trial. Let's run it and see what we get. As expected, we can see that the distance does grow fairly significantly with the number of steps. And now if we stare at it, maybe we can get some intuition. Let's look at this one point way out here in the upper right. We see that's almost 100 steps away and with a total of 10,000 taken. So maybe, just maybe, there's a relationship between the square root of the number of steps and the distance. Let's write some code to see whether that seems to be true. So now we can look at drunk test P1. It's like drunk test P, except in addition to plotting the distances, I'm going to just plot the square root so that we can tell them apart. I'm going to put the distance on a blue solid line and the square root is going to be on a green dashed line. I'm going to use appropriate labels and then produce a legend so that we'll be able to look at the graph and see what it means. Let's run it. See what we get now when we run drunk test P1. Sure enough, the two of them seem to track. They're not identical, but they're pretty close. It does appear that the mean distance is just consistently a little bit less than the square root. We could think that perhaps that's a result of just randomness, but I've done this a lot of times and it seems to be pretty consistent. But I'll leave it for now as an exercise to the student to try and think about why we might have this small but consistent difference between the mean distance and the square root. Instead of dwelling on that, what I want to do is go back to something we started with when we first began to put this simulation together. You might recall that rather than just implementing a drunk, we implemented two classes, drunk and usual drunk. We did that so that we could later experiment with different kinds of drunks. And that's what I want to do now. So here's the usual drunk, the class we've been simulating thus far. I want to look at a small variant, somebody called a cold drunk. This is a drunk that hates to be cold, and when forced or when randomly taking a step north, rather than taking a full step of 1 unit, he's a little bit reluctant, and so he only takes 0.95 units. Not quite a full step northward. Obviously, we're working in the northern hemisphere, I guess, where north is where it's colder. Suppose if we wanted to do it in the southern hemisphere, we'd have to change it. Now, I want you to think for a minute about how much difference this should make. Is the difference going to be small? Because after all, the difference between 0.95 and 1.0 is not great. And what direction is it going to be in? Is the distance going to be larger or smaller? You might think the distance will be smaller because after all, a quarter of the time the drunk is taking a slightly smaller step. Or you might think it would be larger because the southward steps are not fully canceled by the northward steps. It's not obvious to me, but that's why we can run a simulation to find out. But before we do, I want to look at one other kind of drunk, a different subclass, calling this an E-drunk for Euclidean drunk. You may recall that in our first implementation, the usual drunk, we simplified things by saying the drunk moved either east, west, north, or south. I now want to remove that simplification and allow the drunk to, say, move on a diagonal. To do that, we're going to use a function we haven't looked at before called random.random. That's probably the most important function in the random class. It's a function upon which all the others are built, in fact. And what that does is it returns a random number in the range 0.0 to 1.0. So we'll first get delta x in that region. Now notice that this will always be a positive number, and we surely don't want our drunk to always be wandering eastward. So we'll take another use of random.random, and we'll say if it's less than 0.5, then we'll make delta x equal to minus delta x. Now you might think, oh, this is introducing a little bias because I've said less than, and suppose it hits 0.5. Well, the truth is it will almost never be 0.5 because the number of floats in this range is so large, it's highly improbable you'd hit any particular one of them. Then we'll do the same thing over here for y. And so now we've got new values, and then we'll return the tuple delta x, delta y. Almost ready to run a simulation, but not quite. Why not? Well, let's go back and look at what SimWalks did. You'll notice that I did something that perhaps I shouldn't have. I hard-coded usual drunk in this code, so that in fact I have no way to experiment with any drunk other than the usual drunk. Probably not good programming, and fortunately something that's easy to fix. So let's now go over and look at the code where I fix it. So over here we see a modified version of SimWalks. I've added an extra parameter, D class, short for drunk class. And now when I instantiate it, rather than using the constant usual drunk, I use whatever value this parameter has. Once again, we see the great leverage we get in Python from the fact that everything, including classes, are first-class objects, so we can use them in a uniform way. And then I've made a modification to drunk test as well. Let's look at it over here in the PowerPoint so I can draw on it. The interesting part is I've added this loop. I'm going to iterate over the three classes of drunk, usual, cold, and E. For each class, I'll start with mean distances equal to the empty list, and then I'll run the simulation as before, getting the average distance of a walk for that kind of drunk. And then, still within this loop, I will produce a plot for the drunk, and I'll use as a label for the plot the name of the class. So we see yet another underbar operator. dClass.underbar name will return the name of the class, and that will allow me to have a legend that tells us which plots correspond to which class. And then there's some boring code afterwards that just produces the plot. We won't bother with that. All right, let's come over and run it. See what we get. Wow. This might not be what you expected. You can see here the top line, the green line, is the cold drunk. He seems to be moving considerably further than the other two, despite the fact that a quarter of the time he's taking a shorter step. This is the usual drunk, behaving as we saw last time. And then the E-drunk seems to be moving kind of like the usual drunk, but not really as far. And in fact, the distance seems to be getting greater. Should we believe that these results are dispositive, or are they just a fluke? There is randomness here. They could just be a fluke. Well, over the next few weeks, we'll look at mathematically sound ways to answer this question. But for now, I'm just going to run another trial and see if we get kind of the same answer. So I'll run another trial of 50. Pretty much the same thing. The distances are a little bit different, but the trend is almost identical to what we saw before. Now you can go back and ask, is this what you expected? If not, think about why not. If you think hard enough, you'll be able to come up with some theory, maybe a good one, maybe not a good one. But I think this would be a really nice topic for discussion on the 600X forum. Why do these plots look the way they do? Okay, let's wrap up this lecture by thinking about what I want you to carry away from this segment. So the first thing is that starting with abstract data types makes life easier. Because we had locations and drunks and fields, we could, in a very straightforward way, write the simulation itself. We saw that subclassing is useful. Because we started with the abstract class drunk, we could then create several subclasses that would let us explore the behavior of different kinds of drunks. We saw that once the basic structure is in place, we can try different experiments. We can play with different length walks, with different kinds of drunks, etc. And finally, we saw that we can use plotting to get insight into trends, how things change with respect to the number of steps. Okay, thank you.